So good morning. So let's get started. So welcome to the session on lattice-based zero knowledge. We'll have 3 talks this session. And the first talk is on lattice-based zero knowledge proofs and applications, shorter, simpler, and more general. This is a talk by Vadim Lubashevsky, Con Nguyen, and Maxime Plancon. And if you have seen the preview talk, this is the one with the rap video. So we're all heavily awaiting your talk. So whenever you're ready.
Mic check. Oh, it works great. So thank you very much for the introduction, and thanks everyone for coming this early. So hi, my name is Khan, and today I'm going to talk about lattice-based zero knowledge proofs and applications. Okay, so let's start with zero knowledge proofs. I guess everyone is familiar with this concept. So we have some statements like this, and we have 2 parties, the prover and the verifier. And the prover wants to convince the verifier that the statement is true. So the prover has the corresponding witness, and they engage in an interaction where they say messages to each other, where at the end, the verifier outputs accept or reject, which means that the verifier is either convinced or not convinced about the validity of the statement. Okay, so we have a few properties of zero knowledge proofs, such as completeness, which says that if the witness is valid, then for an honest prover, the verifier should accept. Then we have soundness, which says that if the witness is invalid, then for any cheating prover, the verifier should reject. And last but not least, we have zero knowledge, which says that the verifier shouldn't learn any information about the witness from the interaction. Okay, so well, due to the significant progress in building quantum computers, there has been a tremendous amount of interest in making cryptographic primitives quantum safe. And this is highly evident with the ongoing NIST post-quantum competition, where very recently 4 schemes were selected by NIST for standardization, out of which 3 are based on lattices. So why are they interesting? Well, not only do they offer relatively small sizes, but they can be very efficiently implemented in practice. So it seems that lattices are a natural candidate for building more privacy-oriented primitives, such as zero knowledge proofs. However, if we look at the current state of the art quantum safe zero knowledge proofs, then the situation is pretty interesting. So we have very nice hash-based proof systems, such as Ligero, Aurora, and Fractal, where the latter 2 achieve polylogarithmic proof size asymptotically, and concretely, when the witness size is around 1 million, then it's around 200 kilobytes. However, if we look at the situation in the lattice setting, well, it's not so great. So, okay, even though we have a few nice constructions which are sublinear, well, the best one is the lattice adaptation of bulletproofs, they are still of theoretical interest. And the main reason is that if one were just to instantiate them with concrete parameters, then they could easily reach tens or hundreds of megabytes for proof size. However, as we can see, well, in the next 2 talks, actually, that it's a very active area of current research, and there are already schemes which can achieve some concrete proof sizes. However, we can see that it's still far to be comparable with the hash-based proof systems. So in terms of the possible research directions in the lattice world, the first one is pretty clear, is just to construct succinct zero knowledge proofs from lattices, which concretely can be comparable with the hash-based constructions. However, I would like to introduce you to another angle or another research direction, which is to focus on small statements, which we call the interesting statements, for which we can construct practically efficient. So asymptotically, they can and will be linear in the witness size, zero knowledge proofs, which can concretely achieve small proof sizes, let's say less than 50 kilobytes. So this is what we focus on in this talk. So what are the interesting statements? Well, if one were to construct some privacy-oriented primitive from lattices, it makes sense that at some point, some user or some entity will want to prove knowledge of some short vector in the lattice. So at the end of the day, we consider statements of the form AS is equal to U. So some equation over some ring R, let's say integers modulo Q, or some polynomial ring, as usual. And then the S, which will be the secret information, is some short vector. So it has either small norms, small coefficients, and so on. Okay, so this is here we have some concrete example, which we will call the benchmark statement. So prove that AS is equal to U, integers modulo Q, Q is around 2 to the 32, length of S is 2048, and SIs have ternary coefficients. So now if we first look at the hash-based proof systems, then the Aurora gets around 70 kilobytes. Then we have the permutation-based or combinatorial proofs, where the best one achieves around 200 kilobytes. And the last group, which I call like NTT, CRT packing proofs, they already achieve less than 50 kilobytes. So in the next few minutes, I'll try to give some motivation and discuss advantages and disadvantages of these NTT packing proofs. Okay, so we need some, well, technical overview for that. Okay, so consider the standard polynomial ring, RQ, ZQ of x modulo x to the d plus 1, where d is a power of 2, and now we want q to be 1 mod 2d. So why is it interesting? Because then we can write x to the d plus 1, write it as a product of linear terms, x minus r1, x minus r2, up to x minus rd mod q. And we will call these ri's roots of unity. And now, given the polynomial a in RQ, we can define the entity of A, which stands for number theoretic transform. We define entity of A as the vector A hat, which is just evaluations of A in the roots of unity. So A of R1, A of R2, up to A of RD. So we have a few nice properties of the entities. So the first one is like pretty simple. It's like entity of A plus B is equal to entity of A plus entity of B. The second one, let's say slightly more interesting, is that entity of A times B over RQ is equal to entity of A, component-wise product entity of B. So the main strength of using the entity packing technique is that we can efficiently prove that coefficients of a vector lie in some specified, some fixed range. So to showcase this idea, suppose we have some vector S, and we want to prove that it has binary coefficients. So the idea is that we can write this vector S, S1, S2 up to SD, let's say, and I can find the so-called inverse entity. So I can find the polynomial S check such that entity of S check is equal to S, and then I can subtract 1 as well. So I have entity of S check minus 1 is equal to the vector S1 minus 1, S2 minus 1 up to SD minus 1. And now if I multiply these equations, then we see that the vector S has binary coefficients if and only if the vector on the left-hand side is a 0 vector. And on the right-hand side, we're just using the homomorphic properties of entities. So we have entity of S check times S check minus 1. So we actually reduce the problem of proving the binary to proving, well, the product proof. So we prove that S check times S check minus 1 is equal to 0 over RQ. So how do we do this? We follow the commit and prove approach. So we commit to S check, we send a commitment to S check, and then we prove some relations of S check. However, here is some caveat. So even though the vector S had small coefficients, well, actually binary, the polynomial S check might have actually large coefficients. So you can't really use the standard I-tie compressing commitment scheme, but instead we need to use a slightly more advanced commitment, which is the BDLOP homomorphic commitment. So we committed to it using BDLOP. And now the idea is that, okay, I have some protocol. At some point in the protocol, the verifier sends some polynomial alpha, and we send the masked opening of S check, which is Z equal to Y plus alpha S check, for zero knowledge. And then the verifier can compute Z times Z minus alpha. So, okay, so why is it interesting? Because if we write this equation as a quadratic equation of alpha, then the quadratic term is literally what we want to prove it's 0. So we have this term S check times S check minus 1, which is in the quadratic term. So in the end, we just want to prove that the quadratic term in Z times Z minus alpha vanishes. So to do this, well, we commit to Y. Then we commit to the constant and to the linear terms in Z times Z minus alpha. Then given the challenge alpha, I output Z equal to Y plus alpha S check. And then there are two things. First, we want to prove that Z is well-formed, that Z is indeed Y plus alpha S check. And to do this, we use the homomorphic property of the commitment scheme and prove that Z minus Ty plus alpha Ts is a commitment to 0. And then the second thing is actually what we wanted. So we want to prove that the quadratic term in Z times Z minus alpha vanishes. And to do that, we prove that Z times Z minus alpha minus T0 plus alpha T1 is a commitment to 0. So this is like a brief overview of the product proof. So if we want to also prove some benchmark relation, we also want to prove the linear stuff, like some linear equations. So let's say AS is equal to U. So I'm not going to provide the whole protocol just like before, but like some intuition. So again, if the verifier sends alpha and we send z equal to y plus alpha as check, then the key idea is that if alpha is an integer, then we can apply entities on both sides to obtain z hat equal to y hat plus alpha s. And this is going to be s by construction. And then because we have s on the right-hand side, we can multiply by a. And we have az hat is equal to ay hat plus alpha u. So the idea is that the verifier, before sending the alpha, the prover will send ay hat. The verifier sends alpha, we send the z, and then the verifier just checks that az hat is equal to ay hat plus alpha u. So that's the intuition on the linear proof. So that's basically the BLS 19, Yang-Genal 19 protocol from Crypto 19. So with this protocol, we can prove, so the authors proved the benchmark equation in less than 400 kilobytes. So what are the bottlenecks of this approach? So there are a few disadvantages. So the first one is that we have to use the BDLOP commitment to commit to this S check. And it is relatively expensive. And the reason is pretty simple, because the size of the commitment is linear to the message size. So if the message is long, then the commitment is long as well. So the second thing is like a more technical thing. So, in these protocols, at some point, we want to prove validity of the commitment, right? So we perform some opening proof. And as standard thing in lattice-based zero-knowledge proofs, we need the condition that for the challenge space for any two distinct challenges to be invertible over the ring. And because we have x to the d plus 1 split into the linear terms, well, picking such a space, such a set which has large size is a bit challenging. So the authors only picked the set of size 2D. So the soundness error is around 1 over 2D. Next thing is that the prover had to send the vector z and commit to the y in the clear, which could have the same length as s. So again, if s is long, then sending this is also expensive. And lastly, well, if we want to prove some degree k equation, the prover has to send these k garbage commitments ti. So in the previous slide, we had degree 2 equation, and the prover had to send t0 and t1. So some of these things got improved. So first of all, we have the ALS 20 paper where they reduced the soundness error from 1 over 2D to 1 over Q. They proposed a new product proof where we don't need to send this Z and commit to the Y, which is nice. And also they reduced the number of garbage terms by 1. However, if we still want to prove the benchmark equation, we still want to do the linear proof, right? And for this, well, using the previous technique, we will still need to send the Z and commit to the Y. So the follow-up work, ENS 20 presents a new linear proof where we don't need to send the Z and commit to the Y. And by combining ALS 20 with ENS 20, we obtain a nice framework which can prove, let's say, the benchmark statement in less than 50 kilobytes. However, okay, it's nice, but what are the bottlenecks of this technique? Well, we are still using the BDLOP commitment, right? And well, the soundness error is around 1 over Q. So this opening proof part, it needs to be repeated for soundness amplification. And when Q was like 2 to the 32, then this part would need to be repeated, let's say 4 times to achieve negligible soundness. And we can see that it's all the consequences of using the NTT packing technique. Why? Well, because we wanted to pack things into the entities, we had to deal with this S-check polynomial, which had large coefficients. And to commit to it, we had to use the BDLOP commitment. And also because we have this x to the d plus 1 being a product of linear terms, the soundness it will be around 1 over Q. So, well, the question is if we can construct a protocol without using these NTT packing techniques, which are the limitation of the protocol. So you could guess that if the answer was yes, then I probably wouldn't be here. So here we have the protocol. So in the paper, we present new lattice-based zero-knowledge framework where we don't need to rely on the NTT packing technique. And this comes with 2 immediate consequences. So the first one is like, it's one shot. So I'm saying almost, so there is like one part of the protocol where we need to repeat. However, for practical instances, this doesn't cost much. And also we can use a compressing commitment. So it's fine for us to commit to long vectors as long as they have small norm. So here is the roadmap. So the first thing is we introduced the ABDLOP commitment, which, as the name suggests, combines the ITI and BDLOP. So the nice thing of combining these two is that if we want to commit to a long vector with a small norm, then we can put it in the ITI part of the commitment scheme so that it's compressing. However, we could see in the previous slides that sometimes we want to commit to these garbage terms, like the intermediate auxiliary polynomials, which definitely don't have small norm. And for those, we will commit them in the BDLOP part. And because there are not many of them in practice, then it's fine. So that's like a nice combination of these two commitments. So I hope you're still with me. So the second thing is the proving quadratic relations over RQ. So suppose we commit to some long vector S, and we want to prove that, let's say, S transpose S is equal to 0 over RQ. So, well, to do this, well, we can simply adapt the ALS20 protocol. And, well, you can just believe that it's simple because in the ALS20, they deal with BDLOP commitments. Here we have ABDLOP commitments, so it's pretty similar. However, we extend this approach to also prove quadratic equations which involve automorphisms. So I know it sounds a bit random for now. Why has it been interesting or useful? So it's, instead of proving like quadratic equations like S transpose S equal to 0, we can prove that for some public automorphism, S transpose sigma of S is equal to 0. So, but I hope in the next slide, it will be more visible why it's interesting. So the next step is we prove inner products over ZQ. So just first thing I want to say is that when I say inner products, I mean that, so because these things here are polynomial vectors, when I say inner products, I mean take the coefficient vectors and do the inner products on them. So the inner product is over ZQ and not RQ. So suppose I commit to some long vector S and I want to prove that the inner product of S and some public V is equal to 0. Or even the inner product of S with S is equal to something, to B. So to do this, we use a pretty nice fact, which has a very simple proof, that there is a nice automorphism sigma such that for any X and Y, the inner product of X and Y is the constant coefficient of the polynomial X transpose sigma of Y. So we kind of shifted the problem of solving things, of proving things over ZQ to proving things over RQ. So for example, if I want to prove that the inner product of X and Y is equal to 0, I just prove that the constant coefficient of X transpose sigma of Y is equal to 0. And then to prove that the constant coefficient of a polynomial is 0, we can adapt the technique from ENS20 along with the product proof with automorphisms over RQ. So I hope it's clear why why this product proof with automorphisms is useful, because the polynomial for which we want to prove the constant coefficient contains the automorphisms. So that was the main motivation why we wanted to extend these quadratic equations. Okay, so we know how to prove equations modulo Q. That's great. We can prove quadratic equations. We can prove inner products over ZQ. But in many interesting statements, there is some part which holds over integers. Like we want to prove that the coefficients are binary, or we want to prove that the norm is something. We don't want to prove that the norm is less than B mod Q, right? So to this end, we apply approximate range proofs, which in short allow us to prove that some vector has approximately small coefficients relative to the proof system modulus Q. So why is it useful? Well, because let's say if I want to prove that the norm of S squared is equal to B, first I can prove that the norm of S squared, which is the inner product of S with itself, is equal to B mod Q. And then if I prove that S has approximately small coefficients, then I show that there is no modular overflow around, so we can indeed prove that the norm of S squared is equal to B. So that's how we prove the norms, and also that's how we prove that the vector has binary coefficients. Okay, and then we just obtain the framework by combining all these ingredients. So I don't have much time to discuss all of the applications, but just like a simple benchmark type statement. So just so proving knowledge of a modular FWE sample. So what I mean is, prove that you know small s and e, such that as plus e is equal to u. So thanks to the fact that we don't use these NTT packing techniques, we reduce the proof size from 33 kilobytes to 14, which is more than a factor of 2. So in the paper, we also have many other applications, but I think I'm out of time. But we have verifiable encryption, group signatures, and so on. So we just show how to apply this framework in constructing more advanced primitives. So so I will be happy to discuss the details in person, but that's the end of my slides. So thank you very much for listening.
Great. So thanks for the very nice talk. We have a couple minutes for questions, so please come up to the podium or chat on Zoom, please.
Can you say something about what's the interesting statement? I mean, most of what you said looks like you can prove any linear and quadratic relations on a bunch of variables.
Yeah.
Where does the, which is sort of generic, where does the efficiency constraint? I mean, suppose I have an arbitrary system of linear and quadratic relations. What properties does this thing needs to have so that it's indeed small and fast and everything?
So we can indeed prove like linear stuff and quadratic stuff, but the thing is that we don't want to prove like big statements, and the reason is that the proof system is still, the proof size is still linear in the witness size. So if you want to prove like something big like R1CS, for like when I had this comparison with other works where the witness size is 2 to the 20, then this could easily reach like megabytes. So I guess it is kind of generic enough, but we want to have the statement to be like still kind of small. Oh, sorry. Yeah, small witness. Yeah, sorry.
So in the previous slide, so here you're comparing this proof size of these different schemes, but so these are different schemes, so arguably they're using different parameters in the underlying problems. So I assume this is done for some common level of security.
Everything is for 2 to the minus 128.
128, okay.
Cool. Do we have any more questions? If not, let's thank the speaker again. All right, so our next talk in this session is on lattice-based snarks, publicly verifiable, pre-processing, and recursively composable. This is work by Martin Elbrick, Valerio Sini, Russell Lai, Giulio Malavota, Sri Aravada Siragajan, and Valerio will give the talk.
Hi, thanks for the introduction. So as said, I will talk about lattice-based snarks with a bunch of nice properties. I joint work with Martin, Russell, Giulio, and Aravind. So the structure of the talk is the following. So I will first recall the definitions of succinct non-interactive argument of knowledge and vector commitments, what we know about them in the literature, and how these two primitives relate to each other. In particular, I will show how we can compile a vector commitment with enough properties into a snark. And then in the main part of the talk, I will describe how we obtain a lattice-based vector commitment, which supports opening to polynomial maps by translating a pairing-based construction to the lattice set. And this way, we will also introduce a new set of assumptions. In the end, I will also mention some other results that we have in the paper. Okay, so let's start with the first part. So SNARK stands for Succinct Non-Interactive Argument of Knowledge, and they are a system defined with respect to some MP language L. And the SNARK for a language L is defined by 3 algorithms: setup, prove, and verify. And the interface is the following. So we have a communication between a prover and a verifier. They both receive some public parameters by running the setup algorithm. And then whenever the prover wants to prove to the verifier that some statement is in the language, using the corresponding witness is going to run the proof to obtain some proof pi. send the proof pi to the verifier, and then the verifier can check this proof pi against the public parameters and the statement and decide whether to accept or reject. This proof system requires 4 different properties. So the first one is completeness. So whenever the tuple statement witness used by the prover actually satisfies the relation defined in the MP language L, then the verifier should accept. On the other hand, we also require some form of security. And in our case, we require knowledge soundness. So whenever the possibly cheating prover makes the verifier accept, then we require that there exists an extractor that extracts the witness corresponding to the statement being prover from such an address. These 2 properties alone are trivial to achieve by having the prover just sending the witness to the verifier. What makes the construction non-trivial are the efficiency requirement that we require. So the first one concerns the communication between the prover and the verifier. And this is what we call succinctness, and requires that the proof size should be polylogarithmic in the size of the statement. And a requirement regarding the runtime of the verification is what we call preprocessing. Here, in an offline phase, the verifier can preprocess the public parameters depending on the statement being proven. And then, using these preprocessed public parameters, the runtime of the verification should be polylogarithmic in the size of the statement. An overview of the snarks that we know from the literature. If we consider publicly verifiable snarks for unstructured languages, so CircuitSet and R1CS, for examples, then we see that if we classify all the construction depending on these 3 properties, so preprocessing, algebraic, and post-quantum, where by algebraic, we mean that the only operation used in the construction are the algebraic operation from the underlying mathematical problem upon which the scheme is built. And by post-quantum, in a very liberal sense, we mean anything that is not trivially broken by quantum computers, so anything that is not based on groups, for example. Then we see that none of the construction achieves all these 3 properties at the same time. And moreover, if you're able to show that, if you're able to construct a snark, which is also structure preserving, so a snark where the relation checked in the verification is supported by the snark itself, then we get a construction that is friendly to recursive composition. So a snark where you can prove knowledge of a snark proof itself. If we instead focus on lattice-based snarks for MP languages, again, for unstructured MP languages, then we see that either we achieve public verifiability or preprocessing. So a natural question is if it's possible to construct a snark that achieves all these properties at the same time. So which is post-quantum secure, publicly verifiable, preprocessing, algebraic, and structure preserving. And this is what we achieved in this work. So we construct a lattice-based snark, which has all these properties, and therefore, as I said, is friendly to recursive composition. And surprisingly, the main and only ingredient to construct such a primitive is a lattice-based vector commitment, which supports opening to constant degree multivariate polynomial. And since this primitive is going to give us a snark, which is a very powerful primitive, with no surprise, we will have to introduce some new but natural lattice-based knowledge and non-knowledge assumption. Okay, so let's now define what a vector commitment with functional opening is. So this primitive was introduced in 2016, and the interface of this primitive is similar to that of a snark. So again, we have interaction between a prover and a verifier. They both get some public parameters by running the setup algorithm. And now the prover can commit to some vector X by running the commitment algorithm, and then send the commitment to the verifier. In a later stage, then the prover can decide to convince the verifier that the value committed in the commitment is such that f of x equals y for some function f supported by the vector commitment and some image value y. And the prover can do this by running the opening algorithm to obtain an opening proof pi and send this proof pi to the verifier. The verifier can check this proof pi against the tuple function image fy and the committed value comp. Again, this primitive will require a bunch of properties. So the first one is correctness. So we require that whenever f of x actually equals y, then the verifier should accept. Regarding the security of the primitive, we have 3 different properties in ascending order of strength. So the weakest one is what we call weak binding, and requires that the prover should not be able to open a commitment to 2 different tuples fy and fy prime with y different from y prime. A slightly stronger property is binding, and here we require that the prover should not be able to prove to open inconsistent tuple fi yi. And the even stronger requirement is that of extractability. And here we require that whenever the prover is able to open a tuple fy, Then there exists an extractor that extracts an x such that f of x equals y, and x is in the commit. Regarding the efficiency requirement, we can ask something regarding the size of the commitment and the size of the proof. The first requirement is what we call succinctness, and requires that both commitment and proof should be in size polylogarithmic in the size of the vector x, but could be linear in the size of the image value y. And the stronger requirement is what we call compactness, and in this case, both commitment and proof should be polylogarithmic in the size of x and y. And similar to the snark, we have a properties called preprocessing, which requires, as before, that after preprocessing the public parameters, the verification should run in time polylogarithmic in the size of x and y. What do we know about this primitive from the literature? So there have been construction supporting opening to position functions. So functions where f of x equals one of the entries of x, and linear functions, so linear combination of the entries of x. And this construction have been constructed from groups of unknown order and peripheral groups regarding the pre-quantum construction. For post-quantum construction, we have construction from Melker trees, recently by Pikert et al., vector commitment supporting positional openings from the hardness of SIS. However, this post-quantum construction do not satisfy the compactness requirement that we stated before. So again, natural question is it possible to construct vector commitments which are post-quantum secure and compact, or which supports opening to more than linear functions? For example, quadratic polynomial. And why would that be interesting? Well, if we get such a vector commitment, then we can compile it into a snark for MP. And the idea is that the satisfiability of a system of quadratic equation is already an MP complete language. So this language is defined as follows. The statement would be tuple Fy, where F is some quadratic polynomial map. And then the witness would be an X such that F of X equals Y. And then if we want to get a snark for such a language, using a vector commitment that supports opening to these functions, the construction will be the following. So the setup will be the same of the vector commitment. And then whenever the prover wants to prove that the statement Fy is in the language, using the witness X, the prover is going to commit to X, and then directly produce the opening proof I for the function F evaluated on X. And then send this commitment together with the proof to the verifier. And then the verifier can check the validity of this proof using a preprocessing phase, offline phase before. And then from this construction, we see that the properties of the snark are in one-to-one correspondence to the properties of the vector commitment. So the correctness of the vector commitment implies the completeness of the snark. The extractability of the vector commitment implies the knowledge soundness of the snark. Compactness of the vector commitment gives us the succinctness of the snark. And then the preprocessing of the vector commitment will give us the preprocessing of the snark. In this way, we reduce the task of constructing a snark for MP to that of constructing a vector commitment with this property. And then now I will show how we did this in our work. So the roadmap will proceed in 4 steps. Since I do not have enough time, I will just describe the first 2 steps in detail and mention what we did in the last 2. So in the first step, we are going to take a blueprint for constructing vector commitments supporting opening to linear function, instantiate this blueprint in the pairing setting, and then translate this construction to the lattice setting. While doing so, we will also map the assumption under which the pairing-based construction is proven secure to the lattice setting, and we will obtain some family of new assumptions that we call K-ring inhomogeneous SIS, or crisis for short. And so in this first step, we will obtain a vector commitment, which supports opening to linear function, which is weak binding and succinct. And then in each of the following steps, we will improve all 3 of these properties. We will end up with a vector commitment with the properties that we required for the component. Okay, so before setting the blueprint, let's set up some notation. So in the pairing word, we will talk about some second group G1, G2, and GT, where G1, G2 will be the so-called source group, and GT will be the target group. They will be all of them will be of some prime order Q. We will use the implicit notation so that the generator of group I will be denoted by per bracket 1 indexed by I. And in this way, we will denote the group operation additively within each group, and the pairing operation between elements of the different source group multiplicatively. And this can be also extended to a vector operation. In the lattice setting, we will have some ring R. We put some norm so that we can talk about the shortness of element in this ring. We will fix some prime modulus Q and also work with the quotient ring RQ. And then in the public parameters of the lattice word, we will have some wide random matrix A and some target vector T of the same height of the matrix A. Okay, so the blueprint for constructing vector commitment for linear function, which is implicit in the literature somehow, is the following. So we will fix some vector V whose length is the same as the length of the vector that we want to commit to. And then we will think of the entries of V as some formal variables, and we will define polynomials and monomials over these variables. We will define some target monomial and a complement monomial. So the target monomial will be denoted by V bar, and in this example, it will be just the product of all the entries of V, all the VIs. And then the complement monomials would be defined for each I and denoted by VI bar, and would be monomials or polynomials such that VI bar times VI equals target monomial V bar. So in this case, the VI bar would be the product of all J's different from I of VJs. Then we will have to define some encoding of the X that we want to commit to and the function F that we want to be able to open to. And we will encode this element as a polynomial P of X and P of F, where the entries will somehow depend on X and F. And we will evaluate this polynomial on the variables V. And the goal of this encoding is such that when we take the product of these two polynomials, we are going to get another polynomial evaluated on V, such that the coefficient of the target monomial V bar is exactly f of x. And then all the other cross term, since we are thinking of these variables VIs as formal variables, will be not in the span of V bar. So for example, we can take the following two encodings. So the encoding of F would be the linear combination of the target complement monomials of VI bar with coefficient given by the coefficient of F. And then the encoding of X will be the linear combination of the VJs with coefficient given by the coefficient of X. And then when we take the product, we exactly get what we want. Okay, so now let's instantiate this blueprint with in the pairing word. So we will proceed in step, checking what we need in each of the step of the vector commitment and add the corresponding elements to the public parameters of the scheme. So in the commitment phase, the prover is going to commit to the vector X using the encoding given by the polynomial P of X. And so what the prover requires is the encoding of these variables VJs. So we will add this to the public parameters. And then whenever the verifier has to check the opening proof, he will have to compute the encoding of the polynomial of the function F. So we need to give the encoding of the complement monomials of VI bar in group 2 in the public parameters so that the verifier can compute that. And then using the commitment received by the prover, the verifier will compute the pairing between these two encoding and then subtract the claim image value Y times the target monomial V bar. And if f of x actually equals Y, then the difference should be not in a span of V bar. And the verifier should be able to check that using the proof obtained by the prover. So the proof will be exactly what is required to this check to hold. So we need to add also the encoding group 2 of this cross term in the public parameters. Okay, so now let's try to translate this construction to the lattice setting, first starting with the public parameters. So these are the public parameters of the pairing-based construction. And then we will map the generators of the group into these two uniform matrices A and the target vector T. We will make all the variables Vj public so that anyone can compute on its own the target monomial V bar and the complement monomials Vijs. And then we will translate the encoding of the cross terms Vi bar Vjs, which are needed to compute the opening proof, into short vectors Uij, such that A Uij is equal to Vi bar Vj times T. So we get that the public parameters of the lattice-based schemes are given by AAT or the Vjs and these Uijs, which are short vectors. And then the construction gets translated as follows. So the public parameters are what I said. Whenever the prover wants to commit to some vector x, he's going to compute the encoding of px of v, but just using the linear combination and the bj's in the public parameter. The verifier is going to compute during the verification the encoding of f using the elements in the public parameters and the function f. Then he's going to multiply these two encoding and subtract the claim image value y times this vector, the target vector v bar. And again, if f of x equals y, the difference should be not in the span of v bar. And this can be checked using the proof computed by the prover. And the proof computed by the prover is going to be just this linear combination of this cross term using these vectors in the public parameters uij. Now that we have the construction, we have to also translate the assumption under which the frame-based scheme is proven secure to the lattice setting. So the assumption under which the frame-based construction is proven weak binding is the following. So given the elements in the public parameters, it's hard to find the encoding of the target monomial V bar in group 2. And then if we translate this to the lattice world, we will have that given the elements in the public parameter, it should be hard to find a short preimage U such that AU equals V bar times T. However, we will have to slightly strengthen this requirement and ask that it's not only hard to find a short preimage of V bar times U, but it's hard to find a short preimage of a small multiple of V bar times T. And this is a member of a new family of assumption that we denoted the K-ring inhomogeneous short integer solution. And why do we believe that this assumption is plausible? So the reasoning is as follows, basically. So without the hints given in the public parameters, the problem should be as hard as a ring SIS or ring inhomogeneous SIS. So the adversary has to find a short preimage of a random vector. And similarly, the only way to use the hints is to perform short linear combination of the hints given. But the vector, the image vector V bar times T, for which we have to find a short preimage, is not in the linear span of the images of the hints given. So these hints should not help the adversary to break the scheme. Now that we translated this construction to the lattice world, we can exploit the structure of the ring under which we are now working to be able to perform more than opening to a linear function and actually achieve any polynomial bounded degree. And why are we restricted to linear functions in the brane setting? While so the problem is that whenever the verifier pairs the commitment with the encoding of f, he ends up with some elements in the target group. So the only functions that he can compute over these elements are linear functions. And so the only functions that the scheme can support are linear functions. But now in the lattice setting, when we product the commitment with the encoding of f, we still end up in the ring. So we can allow ourselves to open function more than linear, so quadratic, for example. So I will briefly talk about the last two steps. So once we have a vector commitment which supports opening to polynomial map, which is weak binding exact int, to get extractability, we have to introduce a knowledge version of the crisis assumption. And this is basically due to the impossibility results of Ventral Wicks, which says that you cannot get an adaptive sound snark in a Peloponnese way from a falsifiable assumption. So we have to introduce some non-falsifiable assumption to get extractability. And then once we have extractability, we can use an aggregation trick that involves embedding some SIS instance in the public parameter. And then whenever the prover wants to prove to the verifier a bunch of functions, instead of proving each function on its own, it's going to compress all these functions using the SIS instance and then prove that instead. And using the extractability, we can get extractability for this multi-version function of the scheme. And to briefly conclude the further results that we have in the work, we studied the hardness of this new family of assumption that we introduced. And in particular, we showed that there exist hard instances of this new family of assumption, where this KM inhomogeneous SIS is the module variant of the ring version. And we also studied relation between different parameter regime for these assumptions. However, I should notice that none of this reduction covers the parameters that we use in our scheme. So actually, the scheme relies on a new set of assumptions. And we also discussed some possible application of our snark, in particular, since the snark supports checking a linear function and quadratic function, it natively supports the verification equation of the GPV signature. And as I said, it's also friendly to recursive composition, given the properties that it has. And with that, I conclude, and I'm happy to take questions.
Great, thanks for the talk. So we have time for 1 or 2 questions. So if you have any, please come up to the podium. So I'll start with one question. Can you comment on whether you can extend your construction to achieve zero knowledge as well?
Yeah, we tried, kind of still working on it. We think it's doable, but not so easy.
Questions? Yep.
Hi, so thanks for your talk. I have a question. So what are the challenges to how to decrease the CRS or like public parameter size from quadratic to linear? Because now it's quadratic, right?
Yeah. So the problem is that so the parameter size increases exponentially with the degree of the polynomial that you want to support. So that's why we restrict ourselves to bounded polynomial of bounded degree.
Okay, thanks.
So one more question. So I think in your talk, you describe almost a general framework for compiling a pairing-based construction into a lattice-based one. Are you able to apply your type of techniques to other pairing-based constructions for which we currently don't have lattice-based analogs?
Yeah, again, we are kind of working on it, and not sure if we can achieve something, but we're hopeful about it.
Okay, sounds good. All right, so if there's no further questions, let's thank the speaker again. Okay, so our final talk in this session will be on practical sublinear proofs for R1CS from lattices by Kaan Nguyen and Gregor Seeler, and Gregor will be giving the talk.
So do you hear me? Yeah, perfect. Yeah, thank you very much for the introduction. I'm Gregor Seiler, and I'm going to present a paper together with Kaan that you all now know, and yeah, who gave the first talk in the session, but of course about a different paper. So now I need to figure out how this works. Yeah, perfect. Okay, so we have seen a couple of zero knowledge talks already in this session, so I don't really have to repeat what a zero knowledge proof system is. Just very briefly, what I want to say is that basically a very common structure how proof systems are constructed is that one uses a commitment scheme to commit to some vector over some finite field, let's call it S, and then somehow the commitment scheme must allow to prove, say, linear and quadratic relations on the vector coefficients. And if one has these two ingredients, then one can actually prove that the vector S satisfies some arbitrary arithmetic circuit. And an arithmetic circuit is just a circuit where the gates are multiplication and addition gates over some finite fields. Yeah, so this is really the setting we're interested in the talk. So we really want to construct a proof system for arbitrary circuits, as opposed to maybe the more specialized view that Kaan had in his talk, where he centered towards yeah, relations or basically statements that are important in the lattice setting. So now if we focus on lattice-based constructions, then Kaan has already gone into much detail here. I just want to repeat that there has been quite a lot of improvements in the last 3 to 4 years in the construction of so-called linear size proof systems. So there, the proof size scales linearly with a witness size, and then if one looks what the proof size is for some particular reference statement that Kaan has also introduced, then basically the situation 5 years ago was that yeah, the state of the art was a proof size of almost 4 megabytes, and then This was improved in 2019 by a factor of 10, and then by another factor of 10 in 2020 and 21. And now Khan presented essentially the last iteration in this development where there's another factor of 2 or so improvement. So yeah, so this is a state of linear size proof systems. And now these linear size proof systems, they are maybe somewhat surprisingly useful in applications. And one very important basically set of applications are privacy preserving cryptographic schemes. So for example, think about a group signature scheme. In the standard construction of a group signature, you need to prove that you know a signature, and a linear size system is really good for this. And the reason is that one can essentially design the underlying signature scheme such that the witness that one needs to prove is so small that the linear scaling of the proof system doesn't matter. And one gets nice basically schemes with very practical sizes in the end. But there's a big drawback to this, because one really has to design or use essentially tailor-made underlying schemes for this, because, for example, the signature schemes need to be standard model. One can't use the random oracle model, because proving the hash function would result in a witness that is much too big. And so one ends up with schemes that would never be used outside of these privacy preserving schemes. So a much better situation would be if one could just use some standard signature, like for example, Dilithium or Falcon, that are now coming out of the NIST competition, and just basically use them as a black box, and then maybe also a black box proof system that just proves these schemes. And so in this paper, this is basically what we hope to achieve, maybe not already with this paper, but in the long run, that we have very practical sublinear lattice-based proof systems, so that we don't have to care about the witness size anymore. And yeah, in this paper, we make essentially the first step into this, that we really have a somewhat practical sublinear lattice-based proof system. And now the question is, what happens to all these techniques that were developed for the linear size system? And in fact, basically everything that we have developed for the linear size proof systems is going to be useful, and certainly used in basically our scheme now, but I think also in the future, these techniques will be useful, and also the insights we have gained. Okay, so now to start to be a bit more technical. So in essentially every lattice-based zero-knowledge protocol, somewhere at the core is what we call an approximate proof. And an approximate proof is the following. So if one has a lattice-based commitment, and this is nothing else than just a linear function, A times S, where S is some vector that has short norm, so we just say that S is short, then an approximate proof is essentially some variant of this Shannon-Lubashevsky sigma protocol, where the prover samples some masking vector y, commits to it by sending AY, and then gets a challenge from the verifier that is a very small polynomial. So all the coefficients are, for example, -1, 0, and 1. And then the prover replies with what we call a masked opening. And this is just y plus cs. And since everything is small, also this mask opening z will be small. So the verifier can check that z is small, and then also this equation az is equal to w plus ct. And then this is the whole protocol. This is sound in that it proves a knowledge of an opening to the commitment, because it is actually special sound. So if we have two accepting transcript, we just subtract the verification equation, and then we get this. Oh, this is what I wanted. Yeah, so if we just subtract two verification equation, we get this equation on the bottom of the slide, or not really at the bottom, this c bar t equals a times z bar. And this is what we call an approximate commitment opening, because compared to the actual kind of commitment, there's this additional factor of c bar, and then also this c bar, this pre-image for a is much longer than s. But it turns out that the commitment is still binding with respect to these approximate openings, and therefore this is interesting. Now, a slightly different viewpoint that turns out to be really useful is what we call a weak opening. So we can actually remove this perturbation factor c bar So for example, a C bar is just invertible, we can divide through, but also if it's not invertible, we can remove this by essentially piecing together many of such equations. And then we actually get a pre-image for T. So T is going to be A times S star, and this S star we call the weak opening. Now S star is not short anymore, but it has the nice property that if you multiply by the C bar, that it gets short. And something like this we call weak opening. And the commitment scheme also turns out to be binding for this notion. Now, this approximate proof is linear sized because, yeah, obviously this mask opening, the Z vector has the same dimension as S, so it's linear in the size of S. So maybe a natural approach to come on somehow try to get to sublinear scaling is that one starts with many commitments. So now we have many TIs, many such commitments, and the idea is that we want to prove them all at once. And something like this we usually call an amortized proof. So we hope that we can prove them all at once with a small total cost. And the protocol for this is essentially the same as this approximate sigma protocol. And the only difference is that the verifier now sends many challenges, so C1 up to Cn, and then the prover replies with what we call the amortized mask opening. So they see where there are many SIs and they're all linear combined with these random challenges. And now this has nice scaling because the Z still has only the length of one of these SI in dimension, but now there are many SIs in this Z. So now we have basically broken the linear scaling. This is also still sound for proving commitment openings because it's slightly more complicated, but not much. So it's not special sound anymore. But what we can do is that for every I, we can essentially get two transcripts that only differ in the corresponding CI, and then we get a weak opening for TI. And then if you do this for all I, we get weak openings for all the TI. So this is kind of the basic building block that we use for our sublinear proof system. But of course, the problem we need to solve based on this is that we need to be able to prove our linear and quadratic relation on the SI vectors. And here, of course, the standard approach is that we use this, this mask opening Z. And for essentially every relation that we prove on or want to prove on one of the SIs, we just evaluate this relation on Z that we view as some formal polynomial in the CIs. And then what this gives us is a multivariate polynomial in the CIs. So the prover can just compute this before knowing the CIs, and he can also commit to all these coefficients in this polynomial. And then basically in the verification, the verifier checks that this is equation, or basically this polynomial evaluated at the actual challenges is correct. And then this gives some probabilistic proof that yeah. So for example, to give some examples. So in the case where n is equal 2, so we only have two secret vectors Si, and we want to prove the scalar product of S1 with itself. We would just use the scalar product of Z with itself and get this nice quadratic multivariate polynomial in two challenges. And most of these terms are not very interesting. This is why we usually call them garbage terms, but the highest degree terms turn out to be interesting. And for example, the G4 term in this relation, which is the term corresponding to C1 squared, in the actual execution will be the scalar product of S1 with itself. Now, to use this primitive, there are going to be two problems in practice. So first, for large n, the number of these coefficients in this multivariate polynomial is going to explode. So this is going to be a large number of terms. And basically, for analyzing this protocol and proving its soundness, we need that in the extraction we can control some of the form of Z. And I will say what I mean by this and how to solve these problems. So first, this problem with the number of garbage terms. So just to in more detail, what the problem here is that if we go from n equals 2 to some large n, then our multivariate polynomial will have a quadratic number of garbage terms, and they are just prohibitively expensive to send or commit to or whatever. So what we do in the paper about this problem is that we basically go from a quadratic number of garbage terms to a linear number by using interaction. And this works in the following way. So if we look at our multivariate polynomial, we can write this essentially as a sum of univariate polynomials in the CI. So we have a sum of univariate polynomial fi that are polynomials in CI where the ith polynomial implicitly depends on previous challenges. So maybe more constructively, in this equation, this first term f0 is just going to be the constant coefficient of our multivariate polynomial, and then f1 contains all the terms that just depend on C1. So this is a univariate polynomial in C1. And then more interestingly, f2 is the polynomial that contains of all the terms of f that depend on C2, but maybe also on C1, but we view this depends on C1 implicitly. So we get a univariate polynomial C2 where the coefficients depend on C1. And then in a 2n+1 round protocol, what we can do is that basically the prover sends the polynomial fi before getting the challenge ci. And if you go back to the example of this inner product of z with itself, what this means is now that we write our polynomial in this form. So this garbage term g0 is now this polynomial f0 and so on. So, and maybe the most interesting term here is this f2 polynomial. So this is now a univariate polynomial in C2, but the coefficient of C2 implicitly depends on C1. And in the protocol, the prover first sends all the terms at the beginning that don't depend on anything, then he gets C1, and then he can actually compute this G23 term and send this together with G5, and afterwards get C2. So already in this very basically degenerate example for n equals 2, we see that we went from 6 garbage terms to 5. So we have some reduction here. And the intuition why this is secure is that essentially the attack that we need to make impossible is that the prover can somehow control the evaluation of the final polynomial at the challenge polynomial, the challenge coefficients, or the challenge polynomials. They're also polynomials, but in the underlying ring. So the reason why he can't do this is that basically all these fi polynomials, they actually multiples of ci. So if basically he wants to introduce some correction there because somewhere earlier in the protocol he didn't achieve what he wanted, all these corrections are going to be disturbed because they get multiplied by the next challenge that the prover can't control. Okay, so this is basically how we solve the first problem, that there's a quadratic number of garbage terms, and then there's the second problem that in the analysis of the soundness of this polynomial evaluation argument, what one needs in the extraction is that one can be certain of the form of this mask opening Z. So what this really means is that in the extraction, I can prove that in essentially almost all transcripts, the Z will be always of the same form with the mask with the weak openings that I've extracted. So all these Si star together with the weak opening for the masking commitment Y star, and then basically the Z only depends on the challenges that vary between transcripts. So now in the non-amortized case, so where n is equal to 1, this is very easy to prove, or relatively easy. So basically one way to see this is that because S1 star, and there's now only S1 star, is a weak opening, we have this polynomial C bar that makes S1 star short. So we can, if we take the Z from one accepting transcript, where basically the Y star is defined such that the equation that we expect is actually true, and then multiply this by C bar, then we get this equation here. This also works, yeah. So this equation here. And then if we multiply by C bar and rearrange this a bit, then on the right-hand side, we get something that is small, because C bar is small, Z is small, and the C bar makes S1 small. So everything here is small. And this means that Y star is actually weak opening again for the masking commitment, and therefore the prover is committed to it. So in basically all accepting transcripts, he always has to use the same Y star. Now, the same argument doesn't really generalize to the amortized case, because in the amortized case, we basically individually extracted all the SIs. So we have weak openings for all the SIs and different C bars, all the SIs. So essentially to make this right-hand side small, where there's now many terms, many SIs, we would need to multiply with many different C bars. and they would compose to something big. So then we can't argue anymore about like bindingness or something. So how do we solve this? It turns out that if basically in addition we have some protocol that actually proves shortness of all the SI. So for example, we have some binary proof, then basically we can use this protocol and reason about that the Z must be well formed again. And the argument goes something like this. So so in the extraction, what we do is we get all these weak openings as I star. And since there's a binary proof, we actually expect that they are all binary. So we can ask ourselves what happens if they don't turn out to be binary. And in this case, there's going to be some last non-binary vector. So let's say this is Si 0 star. And then we can essentially restrict to transcripts where the first challenges C1 up to Ci 0 minus 1 are fixed. So we only look at transcripts where all these challenges are fixed. And then let's say in one of these transcripts, we write Z in this form where we absorb all the terms Ci, Si star for I smaller than I0 into Y. Then we can actually apply the simple non-amortized argument and just multiply by the C bar that makes the Si0 small. And on the right-hand side, we get something small again, because all the later terms, they are small by assumption. So we said that Si0 is the last non-binary vector. And this now implies that Y star is a weak opening for this linear combination of these commitments. So again, the prover is bound to it in all these transcripts with fixed first challenges. And the binary proof now basically collapses to binary proof. So the binary proof in the actual protocol is a binary proof for all the Si, and now collapses to binary proof for all the Si starting from I0. And in this protocol, the prover only has very small success probability because Si0 is not binary. And so basically this case can't happen. And therefore we have well forms. Okay. So with this, I basically finished somewhat deep dive into some of the techniques. There are also other techniques, but I don't focus on them now. Just want to say that now we use this to construct a sublinear proof system. And there's, maybe on a high level, there's not really much to do there, because if you just start with a vector S of dimension m times n, and then split this into m vectors of dimension n, where m is approximate equal to n, we essentially immediately get a square root scaling proof system, because we now have m of these commitments, but they are constant size, they don't depend on n, and proving them has only basically length n, because this masked opening is only of the length or the dimension of the SIs, which are of dimension n. And so since if m and n are somewhat the same, then they will be the square root of the product mn, which is the total number of coefficients. So we can just run this amortized proof. As I explained, of course, in the lattice world, there's only like 90% of the work is kind of finding parameters and optimizing the techniques and so on. But this gives a square root proof system. The problem is that it will not be very concretely interesting, because the proof size will still be relatively big. And so we have a second part in the paper where we basically concretely reduce the proof size by not directly sending these TIs, but by committing to them in a Merkle tree. And then we can use these amortized proofs basically and prove the Merkle tree level by level in some inductive way. And I'm not going into details. Basically, all that I want to say is that if we now compare the resulting protocol to Ligero, and the reason why we compare to Ligero is that Ligero also has square root scaling. So by this, we can essentially argue that our protocol has concrete sizes that are very small for a square root scaling system. Then we see that for R1CS and with 2 to the 28 constraints, so you can just think of like 2 to the 28 multiplication gates, then for about equal soundness error, we get a proof size that is about 3 times smaller than Ligero. And I think now the time is also over and I'm finished. Thank you very much.
Great. Thanks a lot for the talk. So we have a few minutes for questions. So if you have any, please come up to the podium. So actually we have one on Zoom, so maybe I will start with that. So the question is, how does R1CS come into play?
Yeah, so I mean, yeah, I didn't say anything about this. So R1CS is essentially just a convenient language that on the one hand, relatively directly encodes arithmetic circuits. And on the other hand, it's very easy to prove because it just consists of essentially linear relations and one very long point-based product of two vectors. So essentially, as soon as you can prove linear relations and quadratic relations, you can prove R1CS. And yeah, this is basically, it's just for the reason why R1CS is interesting is that it basically provides an API that one can, for example, have good tooling for it, for example, to compile code into R1CS and then prove this with whatever proof system supports the language. And it's also a convenient way to basically compare proof systems because, yeah, it's the same language.
Great talk. So I wanted to ask about the round complexity. Is it also square root?
Yeah.
Okay, I see.
Yeah.
So
So-
if you, sorry, go ahead.
Yeah, sorry.
I wanted so the reason that I asked sort of as a follow-up. So if you were to try to compress the rounds using Fiat Shamir, this would actually lead to like a big security loss.
Yeah, so it leads to a security loss, which is like squared in the witness size. Yeah.
Okay.
So there's like if your witness is to the 28, you lose like 14 bits of soundness. Yeah, because of that.
I see. I see.
Yeah.
Do you analyze this in the
Yeah.
paper?
So essentially, so basically, this is actually why the soundness error goes down exactly like this, because yeah, this comes exactly from this that basically this interactive Schwarz-Zippel argument that we give basically loses 1 bit of soundness in it for every additional basically power of 2 in the constraints.
Okay, thank you.
So I have one more question. So when you compare to Ligero, how does the approver and verifier complexities compare? Because here you're just focusing on proof sizes.
Yeah, so yeah, both of them are. So the verifier is not like sublinear if you want this. So it's a linear size verifier, and also I'm actually not sure asymptotically it's probably quasi-linear in the what is it? So it's either quasi-linear or linear, but let's see. Yeah, I guess what would be more interesting is actually a concrete runtime of the prover, and this is one area where what motivates us to study lattice-based proof systems, because I mean these PCP type proof systems, for example, they have the problem that internally they have very complicated computations and large overhead and large concrete overhead in the computation because, for example, they compute on very, very long code words. And we don't really have this in these types of lattice systems. So there's essentially hope that concretely also, for example, the RAM needed is quite small. But yeah.
Okay, great. So let's thank the speaker again. Right, and that concludes the session.